Hello, ladies and gentlemen. This video is about left Riemann sums. Left Riemann sums. So, if you watch the other videos, you know we're trying to find the area under the curve. I'm going to get very specific today, though, and we're going to talk about this curve in particular. We're going to find, this is a series. This is one of 3 videos, left, right, and midpoint sums. So let's get started. This function right here, this curve, is y equals x cubed. Okay, so that's the function that we're going to be dealing with. And what we're going to try to do is we're going to find a formula and actually find this this left endpoint sum, this Riemann sum. So we have to remember that we're trying to find the area of these rectangles. Now in this case, our n, our number of subintervals, is 4. That's 4 subintervals. That's what we're finding. Now that is usually given to us. It's not something you create. And we have here, there's 1, 2, 3, 4 subintervals. So that's where that's coming from. We know that the area of a rectangle that we're finding is area equals length times width. And our width is going to remain the same throughout our problem, but we have to come up with a formula for that. So our width is equal to, we call it delta x, and the formula we use for delta x is b minus a over n. Well, you ask, okay, what is b and a? Well, this is the start, a, and this is the end, b, of the interval that we are finding the area of the curve. So in this case, this is a 2 and this is 0. So our b minus a is 2 minus 0 over our interval, which we already know, our subintervals, which we know is 4. So in this particular case, our delta x, our width, is 0.5. 0.5 for each one of these widths. Now we have to find our length. Well, in order to find our length is going to be the value at each of these left endpoints. I'm sorry, 1, 2, 3, 4. So that's going to be our length. And how we find that is by plugging this particular x value into our function. But we need to come up with a general form for that. So we are going to find, again, our length is going to equal f of x sub I, where I, it represents which rectangle we're talking about. So that's our length. But before we can do that, we need to define what x sub I is going to be. X sub I for left endpoints, this is for left endpoints, is going to be a plus I minus 1 times delta x. That formula generates each one of these values of x that we're going to use in our function to find length. So in this particular case then, f of x sub I is going to equal a, which is 0, plus I minus 1, that is always the case, times delta x, which is 0.5. But since we are now plugging into f, our function here, our y, our function f of x, is equal to x cubed. So that whole thing is going to be cubed. It's going to be cubed. Alright, that's not always going to be cubed. If we had x squared up here, it would be squared. If it was 1 over x, it would be 1 over this quantity. If it was some other thing, square root of x, it would be the square root of this quantity. But the left, this would be true for every left, this formula, right here. Okay? So let's keep working here. Alright, we're going to just simplify this to I minus 1 times 0.5 cubed. Alright, that's f of x sub I. So now we're going to set up our sum. The summation. You know what that is? Summation from I to n. But what is n in this case? Well, we're just going to leave it as n now and give the general form of the f of x sub I times delta x. This gives me the length times width, length times width, length times width of however many rectangles given by this value n we have. In our particular case, we know that n is 4. So we're going to put that up top here. So I is 1 to 4. f of x sub I we know is right here for this particular case. So we are going to have I minus 1 times 0.5 quantity cubed times delta x, which in this particular case is 0.5. So this value will give me the value of each of my lengths of each of my rectangles doing a left endpoint sum, and this will be multiplied by the width. You don't believe me? Let's try it. If I plug in 1 here, 1 minus 1 is 0. 0 times 0.5, 0 cubed, 0. That's my first endpoint, and guess what the value of it is? 0. Good. So we plug 2 in there. 2 minus 1 is 1. 1 times 0.5, okay, cubed. If you did that, that's what you would get, this value right here. When it's 3. 3 minus 1 is 2. 2 times 0.5 is 1. 1 cubed is 1. That's very easily verified right here because that's a 1 right there. Okay, that's a 1 right there. So, and the last one, we put 4 minus 3. 3 times 0.5 is 1.5, and cube it, and it'll be this value right there. Okay? So that's what this is doing. This just multiplies by the width each time. This is 0.5 each and every time. Each rectangle has a width of 0.5. Okay? So now what we would do to figure this out is we would plug in those values, 1, 2, 3, 4, 5, and compute it. Alright, so here we go. I'm just going to write the workout here. So it's going to be 1 minus 1 times 0.5 cubed. You know what? I'm not going to waste a lot of time here. We know that this is multiplied by each rectangle, so I'm going to put it outside. And you may have saw that when we were doing some of our summations, our sigma, our property of that. It's just a constant, so it's going to go outside of the sigma. So then we can do this sum inside. 2 minus 1, 0.5 cubed, plus 3 minus 1, 0.5 quantity cube, and 4 minus 1. Now you're going to need a calculator. You don't need it. It'd be beneficial to compute that. Figure out that those values. Once you do that, you add them all up, multiply by 0.5, and you will get, and verify it, 2.25. That is the approximate area under the curve x cubed from 0 to 2, given 4 subintervals using left endpoint sums. Alright, watch it as many times as you want. Look at it. I know you can't love to hear my nasally voice, but we have our number of subintervals, which could change in every problem situation. We have 4 in this case, 4 rectangles. We always use our area formula, length times width. This delta x formula stays the same. However, our b, our a, and our n may change. Here is f of x sub I, which represents the length of my rectangle. It's given by this, a plus the quantity I minus 1 times delta x. That is true for all left endpoint sums. Okay? And you'll see when we do right and midpoint, this formula will change accordingly. And then this is why we do the summation. This little guy is a sum approximation. And I think we already talked about, but just in case you forgot, this is a lower sum. And it's a lower sum because it isn't obviously below the approximation, less than the approximation. Well, I hope you enjoyed this left Riemann sums, this left endpoint sum little video, and please come back again because I will be having I'll be doing the right ones shortly. Okay, so actually I'm going to be doing it right now, but you can come watch it anytime. Johnstone out.